If people have any. Okay, I don't hear any questions or comments, so I'm going to continue today with our discussion of entropy. And today we'll revisit the Joule-free expansion as an example, and then I'll start a discussion on a microscopic view of entropy, which many of you may have already encountered in other venues. So last class, so the last few classes, we've been building up to this thing called entropy. And last class, we considered the case where we have an isolated system, some general isolated system that undergoes an irreversible process. And that's signified by this black curve that's surrounded by this dashed blue line to indicate a very rigid and insulated boundary between the system and the surroundings. And so because it's rigid and it's insulated, we will consider the system to be isolated as it goes from equilibrium state 1 to 2 in an irreversible fashion. And the question really we were after is, what's the entropy change? Now that we've identified the differential form of S as dq reversible over T, and then delta S would be the integral of that over a process, we wanted to ask, what is the change in entropy for an irreversible process? Because the fact is that the way we have defined entropy so far is through the use of a reversible heat interaction with the surroundings. So you can have a system where you have an isolated system where there's no heat interaction, and you will have a process that occurs irreversibly. And we saw this in the Joule-free expansion. That's a very simple yet very powerful example of that. The gas expands into the chamber that had nothing in it initially. And it's irreversible because you can wait and wait and wait, and you will never see the gas go back to the left-hand side of that container or aggregate on a very small volume of the entire volume that's available. So in that sense, we consider that process irreversible. So what we found is that, well, since the system is isolated and the system is undergoing an irreversible process, Q is 0, but we still must assume that there's an entropy change in this isolated system that undergoes this irreversible process. And so in order to do that, we make use of the fact that our definition, well, it's not our definition in the sense it was given to us through analysis of heat engines, that we need to have a process that somehow connects the 2 points in a reversible manner, okay? And as long as we get a process that connects the 2 equilibrium state points reversibly, it doesn't matter whether we go from 1 to 2 or 2 to 1. And that's because S is a state function. So if we compute delta S for one direction, we know the delta S for the opposite direction because it's just a negative of the other, okay? Again, another example of the power of state functions. So in this case, what we did is we constructed a reversible process where the system is no longer isolated, but there is a heat interaction involved. And we need that heat interaction because ds involves dq reversible. So we construct a reversible process in which there's a heat interaction. And in this case, this could be an isothermal process where we say, all right, well, we're going to keep the temperature of the system the same, okay, by either removing or adding heat. Okay, and so remember that heat interaction is what allows you to have a thermostat. So if you're in the lab or wherever and you need to keep temperature constant, you will have to have some heat interactions between the system and whatever your thermostat is. And in this case, the thermostat is the surroundings, because there will, if you have a chemical reaction, for instance, in your system, perhaps you liberate heat. In that case, then, to maintain constant temperature, you're going to have to withdraw heat from your system. And so An isothermal process will involve a heat interaction between the system and the surroundings. And now the system is no longer isolated because you have this interaction with the surroundings. And so in the red path, in this figure, you see that we've constructed some generic reversible process where the system is no longer isolated and where we do have heat interactions, and that heat interaction is reversible now because we've defined it to be so. Okay. So by combining the black path and the red path, we have a cycle, and we can analyze the cycle because we know we have a few results that pertain to cycles and state functions. So if we go from 1 to 2 and then back to 1, 1 to 2 is the black process, irreversible. 2 to 1, completing the cycle back to the original state, is the red process. That's reversible. We know that delta U is ice. And so we went through some analysis of the Clausius inequality, which I'm not going to revisit. But we know that if we go from, let's see, we can, for our analysis of delta S, okay, we're going to do this integral over the cycle. Okay, so really what this is right here, okay, is the integral. No, I don't want to call that delta S. Okay, so my apologies. We will keep it the way it is. So what we were considering, okay, is this integral over the cycle. Okay, this is very important, of this thing called dq over t. And I've been very careful in not putting a reversible. So that integral over that cycle now is just dq over t. There is no reversible yet. Okay. And I can do that. All I want to know is what is dq over t, okay? And I haven't defined this dq over t as entropy yet. So it's okay, everything is fine. So we can split that integral over the cycle into two parts because there was only two parts, the black process and then the red process going back. And those are the only two potential sources of heat interactions. So if you go from 1 to 2, we have an irreversible and irreversible process, but of course that was an isolated system, so there is no heat. There is no Q for that process. Okay? So that integral to go from 1 to 2 of this thing called dq over t, again, I reiterate, there's no stipulation of whether it's reversible or irreversible here. When we get to this point, we know that that process 1 to 2 is irreversible, so now we can put in irreversible. But it was isolated, so that's going to be 0 because Q is 0. Okay. Now the second stage, where now we let the system not be isolated but interact with the surroundings, we can compute that dq over t integral from state 2 to 1. Okay. And since we stipulated that it's a reversible process, we can now say that that Q is reversible. And so we have the integral from 2 to 1 of dq reversible over t. And all of that sum has to be less than 0 because remember, this is the Clausius inequality. And we found for the Clausius inequality that the integral of dq over t is less than or equal to 0 for a cycle. And I'm not going to rederive this. It's in the previous notes. Okay. So because we had that irreversible stage in our cycle, the whole thing now becomes irreversible. And all of this is now less than 0 because it's irreversible. The equality holds for reversible, the inequality holds for, the equality holds for a reversible process and the inequality holds for an irreversible process. So that's great. This guy is not 0, but the first term is 0. And that term that's not 0 is less than 0. Okay, it's negative. Okay, and so we continued this discussion, and I'll leave that part up here. Okay, so we follow the blue arrow. Now I'll add another one. We follow the black arrow. We don't have to worry about the first term in those square brackets that are in blue. So we only worry about that second term that's added to the first term, which is not 0. So the integral from state 2 to 1, of dq reversible over t is less than 0. That's just a reiteration in a more clean form of that equation in blue at the top, in the middle, or at the top of your screen. But we know by definition that dq reversible over t is just ds. I said that at the beginning of the lecture, right here. So what we have then is that this integral from state 2 to 1 of dq reversible over t is really the integral of ds as you go from state 2 to state 1. Okay, here's the definition of entropy. You see that? And so now what we have is this expression, the integral from state 2 to 1 of ds, and that ds corresponds to a process where we're going from 2 to 1, that's less than 0. But we know that the integral is just this, right? We know this is just ds. That's how we define the integrals and deltas of state functions. So that allows us to write then that delta s to go from 2 to 1 is less than 0. And delta s is just final minus initial. So in this case, this is equal to s1 minus s2, final minus initial. That's what delta s is. And that's less than 0, it's negative. Okay, we were interested to go back to the initial point of this discussion in the process from 1 to 2. Okay, what we computed was delta s for 2 to 1. And we saw that delta s for 2 to 1 is negative. Why? Well, right here. Delta s for 2 to 1 is negative. So that must mean, and I think it should be, this is just simple algebra here, that the process 1 to 2 entails delta s greater than 0, which is this expression and this result right here. Okay, and this was a very important result. So I will pause at this point. I want this to be crystal clear for everyone, how we got this. And if it's not crystal clear for everyone, I want people to ask questions. I encourage people to ask questions. Okay, so in this course, this probably last lecture and maybe the last 2 lectures are probably some of the most important ones to understand and have it be crystal clear in your mind, the progression and the logic that brought us to each and every result. Okay. And so it's something to help you study and you know, I'm trying to help you figure out the most important things in the course. And of course, this is in fact a very profound result, and that it's not that I think it's important, it's very profound. I mean, any physicist or you know, scientist realizes this, that the entropy now for the change for an irreversible process, okay, for an isolated system is greater than 0. So we have to say all of these words because that was the experiment that we did, okay? To just say that entropy is greater than 0 would not be correct because we have to specify every single point of the experiment that we did. And in this case, the experiment was, and the question that we were asking or we were interested in is that what is delta S for an isolated system that undergoes an irreversible process? Okay. So for an isolated system that undergoes an irreversible process, the entropy change is greater than 0. Note that there is no equal sign, it's just a greater than sign. Okay, and so this is a very profound result. Okay. And this is what allows people to say that the entropy of the universe, and so this is more like I call it colloquialism. And colloquialism is sort of like a cultural slang, right? It's colloquialism, but this allows one to say that the entropy of the universe increases. Okay? And it's not quite exact, but that's why it's called a colloquialism. Okay, that's why I put it in quotes. Right? Since the universe is isolated, then if we have processes Granted, they have to be irreversible, and majority of them are, right? Because that's real life. Ideal reversible processes are idealization. The entropy of the universe increases. Okay. Any questions? Okay, so far we have then delta S is greater than 0, isolated. So let me just, okay, so we have isolated system. And this is, again, very important. I can't stress it enough. Isolated system 1. Delta S, isolated system, is greater than 0 for all irreversible processes. Okay, so if we have any irreversible process occurring in an isolated system, delta S is going to be greater than 0. Okay, so that's for irreversible. What if you have a reversible process? What if you have a reversible process? Okay, well, in that case, what would the Clausius inequality be? The Clausius inequality for a reversible process would be 0, right? It would have to equal 0 here. Okay, so if you had some process that occurs reversibly in an isolated system, right? This thing would not be inequality, it would be an equality, and it would equal 0, in which case then delta S of an isolated system is equal to 0 for all reversible processes occurring in that isolated system. Okay. Any questions on that? Okay. And then finally, delta S isolated system less than 0 is impossible. It will never happen. The entropy will never decrease in an isolated system. Okay, impossible in an isolated system. Note again that this is all for an isolated system. Okay, if you fail to remember this, you will get confused. So far we've only been talking about isolated systems. If you have a non-isolated system, important, and you'll see this, important, for non-isolated systems, delta S can be negative. Okay. So this is something very, very important. Very important result summarized. And I invite and encourage everyone to actually go through the logic and the thought process that allowed us to come to these very important conclusions, the underpinnings of modern science, essentially. Okay. Okay, any questions? I'm going to go on to an implication of this result. So this is a very important screen, recaps the last few lectures, and the last few lectures are, I would say, very, very important in this course. Okay, so let's go on if there are no questions. So we looked at an isolated system. Okay, so far we've been talking about an isolated system. Let's just take a moment to consider the environment or the surroundings. Okay, so what about the surroundings? Okay, and so this is very simple. We know that the universe is equal to system plus surroundings. This is going back to day 1 or maybe day 2 of this course. That means then that delta S of the universe is equal to delta S of your system plus delta S of the surroundings. Okay. Going back to these very fundamental definitions, and that's why they were so important. I know they were mundane, but now we understand why. Once we understand the very simple, we can make very complex, we can jump to complex things. So let's consider the two cases, right? So for an irreversible process, okay, we know, so if you have a system that undergoes an irreversible process, okay, or there's a process in the universe, okay, delta S of the universe is going to be greater than 0, okay, because everything is in the universe. Right? So if you have a process that occurs irreversibly, the entropy of the universe has to increase, which means then that delta S of the system plus delta S of the surroundings is greater than 0. And that means that delta S of the system is greater than negative delta S of the surroundings. And that's a very important result for an irreversible process. Okay. So it doesn't just, and so like in the case of delta U, for instance, delta U of the surroundings is equal to minus delta U of the system. In this case, for entropy, it's a little different. And so you have to keep that in mind. Okay, so remember, I'll make that note here. Note, delta U universe is equal to, what is the delta U of the universe? Anyone? U is the energy, internal, if you want to call it internal, okay, but this U is the energy. So delta U of the universe for any process is going to be
0.
So delta U system is always going to be minus delta U surroundings, but not so for entropy. And this is what you'll have to really keep in mind, okay, on these problems. And if you understood how we got to this point right here, everything is clear, because we know that for an isolated system, i.e. the universe, we have these inequalities. Okay? So if you have an irreversible process occurring in the universe, knowing that delta S of the universe is an addition of two things, we can relate those two things. Okay? And we know that an irreversible process in an isolated system, i.e. the universe, has to be greater than 0. That means that addition of two things has to be greater than 0. And that gives us a relationship between delta S system and delta S surroundings. Okay? And this is different. And I will put this in a box so you can think about this and make sure you understand the difference here. Delta U of the universe is 0, right? Universe, we said, this is conservation of energy, the first law. Okay. So this is the difference. Okay. Now, if you have a reversible process in the universe, we know that delta S universe is equal to 0, and that's just delta S system plus delta S surroundings. And in this case, delta S system is equal to minus delta S surroundings. Okay. But only in this case do we have this. Okay, and of course, delta S of the universe is not going to be negative, so we don't worry about it. All right, any questions, comments? Everything crystal clear so far? Okay. So this is another important result. I hope everyone will contemplate this and make sure this is also crystal clear in your minds. Okay? This is worth taking some extra time to make sure it's well imprinted in your neural pathways, okay? In addition to these results. And why, okay? Importantly, why? Okay, let's move on. If there are no questions, I want to do two examples. Okay, I want to do two examples. Let's do some examples. These are simple examples, okay? The first one, we're going to consider two objects, two blocks, okay, that are in an isolated system. So let's say we have our container, it's insulated, and it's a rigid container. Okay, so this is a rigid, insulated container. Okay, so we know that there's going to be, and our system is going to be inside it. Okay, so the system is inside, so that means there's no work or any heat interactions between our system and the surroundings. Okay, so our system is going to be two blocks or two masses, whatever you want to call them. Okay, here's the first one, and that block is going to be at temperature T1, and we have another block at temperature T2. Okay, initially. So we have two blocks. That's our system, okay? And that system now is put in this rigid, very well insulated container so that there's no interaction in terms of heat and work between our system and the surroundings. Okay? And as you've seen in thermodynamics now, that we can do all sorts of games. These are virtual games. What we're going to do now is take those two blocks and connect them. So the two blocks, one is at temperature T1, the other one is at temperature T2. At the moment, we won't worry about which temperature is higher or lower. We'll just say that one is at T1 and one is at T2. T1 does not equal T2. So this is our initial state. Our initial state has the two blocks separated, okay, at T1 and T2. T1 does not equal T2. Okay, so this is important. That's our initial state. T1 does not equal T2, and it's at equilibrium. And then what we're going to do is just bring the two blocks together as our experiment. And so what we'll have is this. So we'll have block one at T1, and this is the start of our experiment. Okay, the experiment starts the moment we put them together. Okay, again, we have rigid insulation around it. Okay, so we start with the two blocks apart, one at T1, one at T2. We bring them somehow, okay, I know this is isolated, but we somehow bring them together so they're in contact. At that point of, the moment of contact is when the experiment begins. That's when things are going to start changing and things are going to happen now, okay? And so what's going to happen is there's going to be heat flow. These are rigid blocks. Okay, so they won't deform or anything like that. The only thing that's going to happen is there's going to be heat flow between the two blocks because they're at different temperatures. Okay? And there's going to be no heat flow out into the environment because we have an insulated and a rigid box. Okay, so that heat, any heat flow that occurs or heat interactions that occur are going to be between the two blocks the moment we put them together. Okay, so let's sort of take this and compute the entropy change of this process, okay? Let's compute the entropy change of this process. Once we put these guys together, okay, what's going to happen? What do you think is going to happen in terms of temperature when we put the two blocks together? Anyone? Anyone want to just blurt it out? At the second equilibrium state, what will we observe?
They'll approach equilibrium.
And what does that mean?
Heat exchange until they are both the same temperature, the two
Exactly.
blocks.
Exactly. There will be one unique temperature. That's right. That's equilibrium. They're going to thermalize and they're going to equilibrate once we bring them together. Now, once we reach that state, right? Once we reach that equilibrium state where they're at the same temperature, if you wait and wait and wait and wait and wait, are you going to see the blocks approach or become or go back to the state where one is at T1 and one is at T2 if we don't, even if we separate them, are you going to see that? Are you going to see one block be T1 and the other block T2?
No.
No, you're not. You can wait forever and you won't, right? So before we begin our analysis of this entropy, what do you think, what kind of a process is this when we bring the two things together and there's heat flow in terms of what kind of a process is this? If you can't see so they start at T1 and T2, you bring them together, they go to some other final temperature, T final, but you'll never see them go back to T1,
Irreversible?
T2. Irreversible, right. This is irreversible. So the process at the final state, we're going to have block, block, and I'll call that TF, right? And so this is our process going on, and it's irreversible. Our system is isolated because it's in a rigid box with insulation. So what do you think delta S should be for this process in terms of magnitude? You only have two choices, right?
Greater than 0.
Right, so delta S should be greater than 0. Let's take a look. Let's start with DS. DS is going to equal, in this case, we have, what we'll do in this example is say, all right, well, we'll compute the entropy change of block 1 and the entropy change of block 2. Entropy, the way we've defined it, by the way, is extensive. Okay. So if we have two blocks, then the entropy is going to be the summation of the entropies of those, or the entropy change will be the summation of the entropy changes of the two blocks. Okay, the way we've defined it. So you can have intensive entropy by dividing by the amount you have, but right now we're going to consider entropy as extensive. That means it depends on what you have there, the amount. Okay, and so ds is equal to ds1, but ds1 is just equal to dq1 over t1, and ds2 is going to be dq2 over t2. Okay. That's ds. Okay. But what can we say about dq1 and dq2? dq1 is just related to dq2. How?
Should be negative.
Exactly. Exactly right. Right? Because whatever heat is lost by one has to be gained by the other. And so ds is equal to, I'm going to just say dq1. Okay, I'm going to take out dq1 from this guy. And that's just going to be 1 over t1 minus 1 over t2. Okay. And so now we can do a little trick, dq1. Okay. And that's going to be, let's see, t2 minus t1 over t1 times t2. All I did was multiply the first term by t2 over t2, and then the second term by t1 over t1. Okay, so to go from here, I multiplied the first term t2 over t2, which is 1, and the second term by t1 over t1, which is 1. And so I get this relationship, t2 minus t1 over t1 t2 for ds. Okay? Any questions or comments so far? Okay, let's consider t1 greater than t2. What happens here? If t1 is greater than t2, okay, ds is equal to, what's the sign of dq1? if T1 is greater than T2. Now remember, dQ1 is the heat flow with respect to our system being block 1. Okay, so now you're considering dQ from the perspective of block 1. If block 1 loses heat, then it would be negative. If block 1 gains heat, it would be positive. So in this case, we're going to say that for our first case, T1 is greater than T2. And so what would dQ1 sign be? SIGN.
Be a negative.
Okay, so dQ1 is negative. So we have a negative sign out here. And then what is this factor T2 minus T1 over T1, T2? And again, we're using absolute temperatures. We're using absolute temperatures. So what is T2 minus T1 in terms of SIGN?
Negative.
Aha, negative. So negative times negative gives us, and that's exactly what we anticipated. Why? Delta S should be greater than 0 because this is an irreversible process. Well, if ds is greater than 0, then the integral of ds, which is equal to delta S, is going to be greater than 0. What about the case where T1 is less than T2? If T1 is less than T2, what is the sign of dQ1?
Positive.
Exactly. So ds is going to be a positive for dQ1. And what about the term in the parentheses, T2 minus T1 over T1, T2? What is that going to be in terms of sign?
Positive.
Positive. Oh, again, ds is greater than 0. Delta S, which is the integral of ds, is greater than 0, just as we anticipated for this irreversible process. And you see here that it didn't matter which one was higher or lower, which block was of higher temperature or lower temperature initially, everything turns out to be self-consistent. Very cool. So in this case, you have an irreversible process. The entropy change is greater than 0 in an isolated system, as it has to be. And so we see here that everything is consistent with our expressions. Okay, any questions? All right, let's do another example. Now we'll okay, I didn't hear any questions, so I'm going to keep going. So now we're going to revisit the Joule-free expansion as another example. Let's revisit the Joule-free expansion. Okay. And in this case, remember, we had this isolated system where we have insulation around a rigid container. And I'll just use half. Right here we have gas initially. Okay, and it's at some temperature T, volume V1 or V left, and some pressure. And here we have vacuum. Okay. And then we remove the partition. And our system is isolated, of course. Why? Because we have a rigid insulated container. So we remove the partition and now we have gas all over. Okay, it's still insulated in rigid box. Okay, we have now volume V final or V2. We have temperature T. The temperature doesn't change. Okay, and we now will have some pressure final P1 and P2. Okay. All right, so that was the experiment. We know that what kind of a process is this in this isolated system? So if we start with our initial state, which is on top, and then we go equilibrium state, and then we go to our final equilibrium state at the bottom. If we wait and wait and wait and wait, are we ever going to see all of the gas go back to the state at the top?
No.
No, so this is what kind of a process?
Irreversible.
Irreversible. So we're going to compute delta S now, okay? And we'll see if this turns out to be irreversible or not. Okay? And in fact, that's going to be the driving force here. Remember I said something about driving force and this asymmetry, that the laws of physics are symmetric with respect to time. Okay. So once I remove this partition, what is the driving force? We know the mechanism is diffusion. Okay. And diffusion is a phenomenological thing. It doesn't derive from anything fundamental. Diffusion is a mathematical model that we use to describe the motion of particles. It's very simplistic, an extremely simplistic mathematical model. But that's all diffusion is. It's a mathematical model. Okay? There's a little bit more. I won't get into the details of that. We'll see it next semester. But the driving force here is going to be the entropy change here. Okay? And we'll see that now as we compute entropy change. So we know that to go from this to this is our 1 to 2. We said that that's irreversible. Everyone agreed. I didn't hear any objections. So what we're going to do is construct a reversible path from state 2 back to state 1. Okay. Now we could do it either way. We're just going to do it from state 2 to state 1. Okay. And what's going to be, that path is going to be isothermal and reversible, of course. It's going to be isothermal reversible compression. Okay. So what we're going to do is isothermally and reversibly, we're going to go from state 2 back to state 1. The system is no longer isolated. Okay, so for this, it's no longer isolated. Okay, we have a thermostat because it's isothermal. So now we have a thermostat, the system is coupled to something external to it so that we can have constant temperature. And as we compress it, there's going to be some heat interaction. Okay, because it's an isothermal process and it's reversible. And we said that the system is an ideal gas, we'll treat it as an ideal gas. Okay? So our system, again, is equal to an ideal gas, something that's modeled by the ideal gas equation of state. Okay. All right. So let's see, what are we gonna see here? What is delta S? Let's write ds first. Okay. So what is delta S for 2 to 1? Okay, this is our question. Okay. ds 2 to 1 is equal to dq reversible because we said we're going to do this reversibly. Okay, as we go from and isothermally from state 2 to 1. All right, let's see. First law. I need to get dq reversible. How to represent dq reversible? Okay, so this is how we do it. We apply the first law. Okay, so we know that du is equal to dq, in this case reversible, plus dw, because the process is reversible. What's du? Well, we have ideal gas. Therefore, du is equal to 0 because isothermal. Remember, U for an ideal gas only depends on temperature, and if the temperature doesn't change, U doesn't change. Therefore, dq reversible is equal to minus dw reversible. Everyone okay with that so far? Any questions? Okay, dq reversible then, dw is just minus pdv. It's reversible, so this is going to be plus ptvn dv, where we now use ptvn from the equation of state. So dq reversible is equal to, p is just nRT dv over v, which is equal to nRT d natural log of v. Temperature is a constant. This is an isothermal process. This is an isothermal process, so temperature is constant. So we have dq reversible. We go back to ds for this process 2 to 1, and that's equal to dq reversible over t. But we just found dq reversible right here. So what we're going to do is plug in dq reversible. And that's going to give us nRT over T d natural log V. V. Okay, the T's cancel. So that leaves us with ds for going from 2 to 1 is equal to nR d natural log V. Okay, any questions? Okay, so now if V2 is greater than 1, we know that, V1, we know that, and let's just say V2 is equal to 2 V1. Let's just say that, okay? Then we can integrate our expression for ds to get delta S for 2 to 1. Okay, this is going from 2 to 1. This is the reverse process, okay? So delta S to go from 2 to 1 is equal to the integral of ds to go from 2 to 1. And we're going from state equilibrium state 2 here to equilibrium state 1. But ds we just found is this guy. So that's just the integral of nRd natural log V. And our initial state is going to be V1, and our final state is going to be 2V1, because we said we're going to go from initial volume V1 to final volume V2. This integral is very straightforward. N is a constant, R is a constant. This is the integral from V1 to V1 of d natural log V, but that just turns out to be natural log V evaluated at 2V1 to V1. And so delta S to go from 2 to 1 is equal to nR natural log, the final state is 2V1 over V1. Oh, I made a mistake, right? It should be the opposite, right? We're going from 2V1 to V1. My apologies. So the limits here are opposite. Did everyone catch that? I'm actually starting with 2V1 and going to V1. I'm compressing it. I'm going back from state 2 to state 1, where I go from 2V1 to V1. I'm almost done. So we just have to change. So we're going from 2V1 to V1, going from 2V1 to V1. And over here, then I have the final state is V1. The initial state is 2V1. This is delta S, but we know that delta S, we can simplify that log is equal to nR natural log of 1/2. This is to go from 2 to 1. But what are we interested in? 1 to 2, right? That expansion. We're interested in the expansion, but that's just going to be the negative of 2 to 1, which is going to be minus nR natural log of 1/2. Okay. And so delta S to go from 1 to 2 is equal to, we can do a few things here. We know what the sign SIGN of log of 1/2 is going to be
Negative.
negative. A negative times a negative in front is going to give us
Positive.
That's exactly what we thought it would be. Or we can write this as, we can take the negative sign and raise 1/2 to the -1, and that gives us nR natural log 2, that's still greater than 0. So both of these expressions give us delta S for this process to be greater than 0. So in this isolated system, the Joule-free expansion, again, I reiterate, you're probably tired of me saying that it's an isolated system, the Joule-free expansion, but we see that delta S to go from 1 to 2 is greater than 0, and we know then that that's irreversible. And the driving force is this increase in entropy. Okay, it's this increase in entropy. The mechanism by which this happens is through diffusion. Okay, but the driving force underlying this expansion for this ideal gas system is this increase in entropy in this isolated system. I'm going to give you a molecular level point of view of the same process. Okay, and in fact, what I'm going to show you is that once we allow, or we say that, okay, well, it's not just some gas. I need to take into account individual particles. They have to be there because this is what we know now. Though Carnot and those guys didn't know it, we know it. What we'll find is when I introduce the approach for, we'll do the Joule-free expansion again using particles as atoms, we will find the same result as this. Okay, and that will give you some insight into what entropy is. At this point, you really have this idea as a mechanical or a prescription for computing delta S. I will give you a molecular level understanding of S in the next lecture. Okay. All right, so any questions? Again, these last few lectures have been quite important and address profound results of thermodynamics. Okay, any questions? Okay, then I'm going to wish you all a happy weekend and I will end the lecture now.
Thank you.
Okay.
Have a great weekend.